Okay, so let's start today. So today we are going to discuss section 5.3, okay, applications of determinants. So can you hear me?
Yes.
Yes.
Okay. So first application of there are actually two applications which we will discuss. First will be the solution of linear equations using Cramer's rule, and the second application is the uh, uh, finding the inverse of the matrix. Finding the inverse of matrix. Okay, so as far as the first application is concerned, the solution of the system of linear equations. So in the solution of the system of linear equations, the formula which you will use will be this: xi is equal to a determinant of ai divided by the determinant of a. So from the system of linear equations, we will determine the determinants using the coefficients of the system of linear equations. So A will be the determinant. So A will be the matrix for the coefficients of the systems of linear equations, whereas A will be the matrix uh, for also for the coefficients of the system of linear equations, but the ith term of the of the matrix will be replaced by the coefficients on the right hand side of the equations. Cramer's rule actually provides a method, such method. So this I can illustrate with the help of examples, and then after that we will find the method. We will find the method for the uh, finding the inverse of the matrix. So suppose if we have the system of linear equation as 14x1 plus 5x2 is equal to 13, and the second equation is 5x1 plus 2x2 is equal to 8 plus 2x2 is equal to 8. So for this system of linear equations, we need to find the values of x1 and x2 using the Cramer's rule. Of course, we can easily find the answer to this equation, but let's just focus on only the Cramer's rule. So in the Cramer's rule, we need these determinants, ai and a. So we need to, first we will set up the matrix A. So matrix A will be the coefficients of these x1 and x2. So 14, 5, 5, 2. So this will be the matrix A. And matrix AI will be corresponding to x1 and x2. So therefore there will be matrix A1. Matrix A1 will be the same as matrix A, but the first column of this matrix will be replaced by the terms on the right hand side. So it will be 13, 8, 5, and 2. And matrix A2 likewise will be this same as column A, but the second column will be replaced by these terms on the right hand side. So it will be 14, 5, 13, and 8. And then the next step will be to find the determinants of these matrices. So determinant of A will be 14 times 2 minus 5 times 5. So it will be 3. Determinant of A1 will be 13 times 2 minus 5 times 8. So it will be minus 14. And the determinant of A2 will be 14 times 8 minus 13 times 5. So this will be how much? 14 times 8. 14 times 8 minus 13 times 5. So it will be
47. 47.
47.
Yes.
Okay. Yeah, okay, yeah, you're correct, but I think I should use 6 over here. I mean, I just made a mistake over here. 6. So, yeah, and then it will be 6 over here also. So 14, 6, and okay, this one. So now it will be 14 times 2 minus 5 times 6. So it will be then minus 2. Yeah, minus 14, and then it will be now here 14 times 8 minus 13 times 6. So it will be 14 times 8 minus 13 times 6. So it will be how much?
37.
Yeah, 37 or 34.
Sorry, 34.
34. So it will be 34. So in this case, x1 will be then determinant of a1 minus 14 divided by the determinant of a, that is minus 2. So it will be plus 7. And then the x2 will be a determinant of a2. So it will be 34 divided by minus 2. So it will be minus 17. So 7 and minus 17 will be the solution. So which we can confirm by putting these values, inputting these values. So this is the Cramer's rule. So we can see one more example. As you can see that the Cramer's rule is provides us some very structured way of solving the solution, but from the calculation point of view, it is not that friendly in this case. So you need a lot of calculations in this case. So suppose in this case, in the second, as a second example, now we have a system of equations in which we have x1 plus x2, x1 plus x2, sorry, x1 plus 2x2 minus x3 is equal to minus 3. And then we have 3x1 minus 3x3 is equal to minus 15. And 7x1 plus 15x2 plus x3 is equal to 4. So in this case, matrix A is then 1, 2, minus 1, 3, 0, minus 3, because there is no x2 over here, so therefore we will place 0. And then the last matrix, the last row will be 7, 15, and 1. The A1 matrix will be, so minus 3, minus 15, 4, it will be in the first row, minus 3, minus 15, and 4, it will be in the first row, and then it will be the other 2, minus 1, 0, minus 3, 15, and 1. And then A2 matrix will be 1, 3, 7 will remain, and then it will be minus 3, minus 15, and 4 will come here, and then it will be minus 1, minus 3, and 1. And then the A3 matrix will be 1, 3, 7, 2, 0, 15, and the last column will be replaced. So it will be minus 3, minus 15, and 4. So in this way, we will get these three matrices. So, and then you can see that we need to find now 4 determinants. Okay. So determinant of A1. Okay. So just find the determinant of A1. So A1, I will expand this matrix by the first row. So it will be 1, and then times the determinant of 0, minus 3, and 15, 1. And then signs will change, plus, minus, and then minus 2, 3, minus 3, 7, 1. So this determinant, okay. So for this 2, we will delete first row and the second column, and then the remaining are 3, minus 3, 7, 1. And then the sign will be plus, minus, plus, so that means it will remain like minus 1, and times 3, 0, 7, 15. So we'll solve it. 0 times 1 is minus 1, and then minus 3 times 15 is 45, and then minus 2 into 3 plus 21, and minus 1 into 45, that is the 3 times 15 is 45, 45 minus 45, so 7 minus 0. So what we get is minus 48, minus 48. Okay, determinant of A will be minus 48. So determinant of A will be minus 48. So what will be the determinant of A1? Yeah, I will not do all these calculations. I have the answers available. I will just write the answer, but of course, you have to do these calculations. So determinant of A1 will be 96. Determinant of A2 will be minus 48. And determinant of A3 will be minus 144. So very well selected values. Then, so therefore x1 will be 96 over minus 48, so it will be minus 2. Similarly, then x2 will be 1, and x3 will be 3. So this is the answer, minus 2, 1, and 3. So for example, if I put this values over here, minus 2, minus 6, and then minus 6, minus 9, minus 15. So, and then of course, I think the answers are correct. So the only thing, the process is quite simple. The only thing is that the calculations are a little bit lengthy in this case, and especially in this case, you can see that you need to find 4 3 by 3 determinants, and which in turn each 3 by 3 determinant is including 3 2 by 2 determinants. Okay, so it's quite an extensive amount of calculations which is involved. And one more thing is that I think maybe you are already familiar with the Cramer's rule from some other classes as well. Do you have any questions about the Cramer's rule?
No.
So you know.
Wait, I have a question. So, what if we have the system with more than like 3, let's say, like 4 by 5, 4 or 6 by 6 matrices? Then the method will be the same, or is there like any other like additional steps for using it? If you have a system with more
Actually, the
than
method will be same. Okay, for example, if you will have 4 by 4 system, the only thing is that the calculations will increase. So for example, if it is a 4 by 4 matrix, if A is equal to 1, 2, 3, 1, 3, 2, 1, 1, 1, 1, 3, 2, 3, 3, 1, 1. Okay, so for example, if this is the matrix, so if we want to expand it for its determinant, so it will be like that. So you can see, you can start from 1, and then what will be that matrix? 2, 1, 1, 1, 3, 2, 3, 1, 1. This matrix 2, 1, 1, 1, 3, 2, 3, 1, 1, and then plus, then minus 2, and then it will be 3, 1, 1, 3, 1, 1, 3, 2.
And then we will need to find the determinant of all the other 3 by 3 matrices. Yes.
Yes.
And they add them up. Oh, okay.
Yeah. So therefore, there is a lot of calculation will be involved.
I mean, there is no like automated method of solving it, like creating a series and anything. Yes. Or is
For
there?
example, what?
Like, is there a method like to make the Cramer's rule for more than like with the higher level of the matrices, just like making them into a series, maybe? Is there any method like
Yeah,
that?
just a minute, 1 minute. Okay. No, I think there is no, as far as the Cramer's rule is concerned, this is the only way to proceed. Okay.
So the only method is just to mechanically solve manually all of the stuff.
Yeah, if you solve manually, then this is the only way. But if you use computer, then definitely you will. It's much quicker. You just have to put the matrix and then give the command, and then it will be automatically calculated. Okay, next use for the determinant is the to find the inverse of the matrix. So finding the inverse. So the formula for finding the inverse using the determinant is that if you have a matrix A and you want to find its in its inverse, so the formula is that it will be 1 over the adjoint of it will be 1 over the determinant of A times the adjoint of A. Okay, So now we know the determinant of A, but what is the adjoint of A? So the adjoint of A is the transpose of the cofactor matrices. Okay, it is the transpose of the cofactor matrices. And then what is cofactor matrix? So the cofactors for a matrix A are given by this formula. So cofactor Aij. So cofactors are certain numbers which are placed at I and j positions of the matrix, such as Cij is equal to -1 power I plus j times the determinant of the minors of those minors of those coefficients. Okay, so this is a very long formula for finding the inverse. And so what is the what are then the minors? So minors are, as we have just previously looked at, the minors are those matrices which are obtained by removing the ith row and jth column, and then whatever the terms are remaining that constitute the minor for that cofactor. So the cofactor is then determined by the determinant of that minor and then multiplying by -1 power I plus j. So actually it's a very, very long formula. Okay, so in this case, so let's apply this formula for some simple case. A is equal to 2 minus 1, 3 minus 3. So suppose we want to find the inverse of this matrix. And of course, there is a much simpler method for finding the inverse of this matrix, which we already know, but that is the method, okay? But now we want to find the inverse of the matrix using the determinant and the adjoint matrix. So let's apply that rule. So first of all, we will find the the easier will be first of all to find the determinant of A. So the determinant of A will be 2 into -3 minus 1 into 3. So it is -6 plus 3 minus 3. Okay, so this is the determinant of A. So that we have found. Okay, so the next is we will need to find the adjoint of A. So for the adjoint of A, we need to find the cofactors. And for the cofactors, we need to find the minors. So in this case, for this simple case, the minors are something like this: M, I, J. So in the form of M. So what are the minors? Minors are, so for example, what is M11? M11 will be this -3. Okay, M11 will be -3. M12 will be 3. So just one by one matrices. Okay, M21 will be -1. M22 will be 2. Okay, and then what are now what are their determinants? So for example, the determinant of theirs are simply for the determinant of 1 by 1 is simply that number. So so we can write their determinants as like -3, 3, okay, -1, 2. So we can write it like this. So -3, 3, -1, and 2. And then we need to multiply these numbers by -1 to the power I plus j. So what is I plus j? So for example, I plus j, it is this is the first row, first column, first row, second column, second row, first column, and then second row, second column. Okay. So 1 plus 1 is 2. So even power of -1 will be plus. Okay. So it means that it will be plus. Similarly, this one will be an odd power, so it will be minus. And then this will be plus or minus 2, 1.
Minus.
Minus, and then it will be then plus. So it means that whatever the value will be here, so we will change the sign accordingly. So it is plus, so it will remain -3. It is minus, so it will be minus. It is minus over here, it will become plus, and then it will be like this. So this will be the cofactor matrix. Okay, this will be the cofactor matrix. So the adjoint will be adjoint. So the adjoint of A will be then the transpose of the cofactor matrix. So we will take the transpose. So that will be the adjoint. So it will be -3, 1, -3, 1, and then -3, 2. Okay. So this will be the adjoint. So now we can find the A inverse. A inverse is equal to 1 over the determinant of A. So it will be -1/3 times the adjoint of A -3, -3, 1 and 2. So just multiply by -1/3, it will be 1 minus 1/3, and then it will be 1 minus 2/3. So this will be the inverse of A. Is this method clear? Is this?
Yes.
Yes.
Okay. So, let's do one more example, which will be for a 3x3 matrix. Okay. So find the inverse of this 3x3 matrix. So it will be 1, 0, -2, 0, 1, 2. Okay, let's do it on the next slide. Okay. We don't have any much space over here. A, so 3x3 matrix. So 1, 0, -2, 0, 1, 2, 2, 2, 1. Okay, so we want to find its inverse. So for the inverse, the formula is 1 over the determinant of A times the adjoint of A. Okay, and let's find the determinant of A first. Determinant of A will be determinant of A will be, so we can expand it from the first row. So it will be +1 times 1, 2, 2, 1. So 1, 2, 2, 1. And then plus, then minus 0 times, so 0, of course, that will be 0. So it will be 0, 2, 2, 1, 0, 2, 2, 1. And then, so it is plus, minus, plus. So it will be, okay, -2. No change for the sign of 2. And then it will be 0, 1, 2, 2. So 0, 1, 2, 2. So now we get is 1 into 2 is 1, -4 is -3. This is 0, and then we get is -2 times 0 times 2 is 0, -2. So it is -2. So what we get is +4. This is +4, -3. So +4 -3 is, we get 1, simple 1. Okay, in this case we get 1. The determinant of A is 1. So for finding the adjoint of A, we need to find the cofactor matrix for A. So for the cofactor matrices, so first cofactor will be C11. Okay, so first cofactor will be C11, and this will be with plus sign. Okay, so that will be with plus sign. So this will be what? So in this case, this first row and first column will be removed. So the matrix left will be 1, 2, 2, 1. So 1, 2, 2, 1. Okay, so this will be minus 3. The second cofactor C21, that is 2, 1 over here. This will be which matrix? Now in this case, the sign will be negative because 2 plus 1 is an odd number, so it will be a negative sign. Remember that the formula for the Cij is minus 1 power I plus j and times the determinant of the minor. Okay, so minor ij. So so this is the symbol for the determinant, and then inside 1, 2, 2, 1 is the minor. Okay, so 2, 1 is now this will be with minus sign, so it will be 0, 2, 2, 1. So it is not 1, 2. No, it is not 2, 1. It will be 1, 2 actually. Sorry, it will be 1, 2. Okay, first row, second column, 0, 2, 2, 1. Okay, so 0, 2, 0, 2, 2, 1. So therefore we will get plus 4. Okay, C13, that will be with plus sign. 1 plus 3 is 4, is an even number, so even power will be plus. And then C13 will be first row, third column. So what we have is 0, 1, 2, 2. 0, 1, 2, 2. So we will get minus 2. Okay. Next, we have C21. That will be with a negative sign because 2 plus 1 is minus. So 2, 1. So 2 and 1. So 0 minus 2, 2, 1. So 0 minus 2, 2, 1. 0 minus 2, 2, 1. So we will get minus 4. C3, C22. Okay, C22. So 2 plus 2 is 4. So it will be with plus sign. So 2, 2. So 2, 2. And then 1 minus 2, 2, 1. So 1 minus 2, 2, 1. So what we will get over here, the determinant, C22?
5.
5, okay. Then C23, it will be with minus sign because 2 plus 3 is 5, and then 2, 3. So 2, 3. So 1, 0, 2, 2. 1, 0, 2, 2. So what we will get is 2 minus 2. Okay. Okay, and then for the third row, so 3, C31, 3 plus 1 is 4 with plus sign. So it will be third row, first column, 0 minus 2, 0 minus 2, and 1, 2. So what we get is C31 is, what will we get?
2.
2. Okay, and C32, 3 plus 2 is 5, so minus sign. And then third row, second column, so it will be 1 minus 2, 1 minus 2, 0, 2. Okay, 1 minus 2, 0, 2. So we will get is minus 2. And then the last one, C33, 3 plus 3 is 6, plus sign. So third row, third column, 1, 0, 0, 1. So 1, 0, 0, 1. So what we will get is 1. So therefore we get the cofactor matrices as cofactor matrix as starting from this C11, C12, C13, minus 3, 4, 2, minus 3, 4, minus 2. Okay, minus 3, 4, minus 2. Minus 3, 4, minus 2. And then C21, C22, C23. So minus 4, 5, and minus 2. And then C31, C32, C33. So it will be 2, minus 2, and 1. So 2, minus 2, and 1. And what will be its transpose? C transpose. It will be minus 3 because for the transpose, the first row will be the first column of this matrix. So it will be minus 3, minus 4, 2. And it will be the second row will be the second column. So 4, 5, minus 2. And the third row will be the third column. So minus 2, minus 2, 1. So this will be the C transpose. And then C transpose is basically the adjoint of this matrix. Okay. And now we know that the A inverse is 1 over the determinant of A. So determinant was actually 1. So fortunately, we don't have to make any changes into this adjoint of A. So actually, in this case, in this particular case, this is the A inverse. So the A inverse will be minus 3, minus 4, 2, 4, 5, minus 2. Okay, so in this way, you can find the inverse of a matrix using the determinants method. Okay, so this is the last example which I wanted to discuss, which I wanted to solve regarding the determinants topic. Do you have any question?
No.
Okay. So I hope it is clear, right? Okay, just give me a second. So with this, the topic of determinants is completed. So since we have some 10 minutes, so we can start a new topic on the eigenvalues. So we have actually completed 5 chapters of the book. There is one section which is left for the row subspaces that I will upload later on. So in parallel, you can see I have also uploaded certain topics which are mostly related with the vectors. Okay, so you can also go through those topics which I have uploaded, but I did not actually discuss in the live class, but I have uploaded those videos as well. So the last I uploaded is about the basis, introduction of the basis. So we will later on, I think in the later chapters, I will introduce more concepts about the basis, especially for the orthogonal basis properties later on. So this is this linear algebra part is a kind of like mixed of the matrix and the vector algebra. So we will also look at vector algebra as well. Anyway, the topic which we are starting now is the eigenvalues and eigenvectors. Eigenvalues and eigenvectors. So it is actually it is an important topic, and the final exam normally have a question from this topic. There is a definite question from this topic, and actually it is a little bit lengthier topic as well. So I will cover it in the next lecture, and then maybe 2 more lectures at least in the next week, or maybe the whole next week also for these eigenvalues and eigenvectors. So what is the eigenvalue? So the definition of an eigen value and eigenvector is from this relationship. So for example, if we have a square matrix A, and we multiply it with the vector U. So vector U is also a matrix. So for example, if we have a square matrix, say n by m, n by n, okay? And then if we have a vector, which is also n by, which is n by 1, okay? Vector is just a single column matrix. So what we will get is the product of this AU will be, we will get an n by n, okay, which is the same as n. And so if we have this vector and then matrix, we can multiply it with by U. And then if for this relationship, since we know that we have a resulting, the result of AU is n by 1. So n by 1 is also a vector. So for example, we have, for the sake of discussion, we say that if we multiply a matrix, okay, by a vector, and we get a vector. So what do I mean? What do I mean by this is that in matrix we have more than one columns, okay? In more than one column, such as n columns, okay? But in vector we have only one column. So if we multiply matrix with the vector, and suppose that they are compatible with each other, okay? For example, matrix has n columns and a vector has n rows. So then we will get a vector, okay? So if associated with that vector, if we can find a scalar that is a multiplication number, lambda, which when multiplied with that u, which when then multiplied with that u, and then both are equal with each other. So then we say that this u is a eigenvector. Then we say that u is an eigenvector. So this is the concept, okay? When we say that u is, in that situation, when AU is equal to lambda u, then we say that u is an eigenvector. And for lambda, we say that lambda is an eigenvalue, okay? Eigenvalue. So certain kind of combinations of A and U will exhibit this type of property. So in this, and then of course in many engineering applications, this type of relationships occur. So therefore, we would like to study those type of relationships. So just as an introduction for the next 5 minutes, suppose I have, as an example, if we say that if A is this vector 3, 1, 1, 3, then show that U is equal to 1, 1 is an eigenvector. Okay, so how we can show that U is an eigenvector associated with this matrix? So as you can see from this relationship, we just have to multiply A by U, okay? And then if we see that whether we can find any constant scalar quantity out of U, then that will be an eigenvector, okay? So just check it, 3, 1, 1, 3, and then multiply by 1, 1. And then what we will get is 3 into 1, so 3, plus 1 into 1, that is 1. 1 into 1 is 1. 1 into 3 is 3. So what we will get is 4, 4. And then from this 4, 4, what we can do is I can write it like this: 4, 1, 1. Do you agree? If I write 4, 4 as 4 times 1, 1, right?
Yes.
Yeah. So, but in this case now 4 and then 1, 1 is that U. So what we have got is, this was A, this was U, AU is equal to 4U. So it means that we have met the conditions for the eigenvectors. Okay. So it means that U is an eigen vector. Okay. And then 4 is an eigen value. Okay. So U is an eigenvector for A, and 4 is an eigenvalue of for A associated with that eigenvector. So this is in this way we have just showed the existence and property of eigenvectors and the eigenvalues. So suppose if just the last example, suppose U is equal to instead of 1, 1, it is 1, 2. So just check if it is an eigenvector or not. So 1, 3, 1, 1, 3, and then 1, 2. So it will be 3 into 1, 3, plus 1 into 2, 2, and then 1 into 1, 1, 3 into 2 is 6. So it is 5, 7. So now this 5, 7, you cannot write like in this form. This 5, 7, you cannot write in this form. So it means that this is not an eigenvector. This is not an eigenvector. Okay. And if it is not an eigenvector, then of course, associated to that, there is no eigenvalue. So what take home message over here is that not every vector is eigenvector associated with the matrix. So that means this type of property is quite specific for certain kinds of vectors. Okay, so that's I wanted to discuss, and then later on in the next class on Friday, we will do some more examples on eigenvectors and eigenvalues, and of course their applications as well. Okay, that's all for today. So do you have any questions?